So on behalf of the Department of Mathematics at Princeton University, it's my pleasure to welcome everyone here for the inaugural lecture of the inaugural Minverva Distinguished Visitor. And we're really appreciative of the Fernholz Foundation who's able to sort of set up this Minverva Distinguished Visitor program, and we're particularly grateful that the way they set it up is sort of extremely flexible, so that we can sort of take advantage of opportunities that sort of come along in different manners. So, and just for your information, the Fernholz Foundation is endowed by Robert and Louisa Fernholz and is directed by Louisa Fernholz, and we're really grateful for the many years long-standing support of the Princeton University Math Department. So now it's my pleasure to introduce Professor Xiaoyu Zhang, who will introduce the Minverva Distinguished Visitor.
Sorry, this is a formality of 2 steps. Okay, it's my great pleasure to introduce with somebody else.
Professor Zhang is the chair of the Minverva committee, so it's the chair.
Somebody else. So it's my pleasure to introduce Andrei Okounkov to give our first distinguished visitor lectures. So I just to make things clear, this is different than this distinguished lecture series. For that series, I have 3 lectures. This one have 10 lectures. And I don't need to introduce Andrei too much. Many people know has much long overlap with him than me. I only 1 year overlap with Andrei. When I was in Columbia, I worked really hard to get him to Columbia. Now I'm working really hard to get him back to Princeton. The title of his lecture is Quantum Group and Cohomology.
So I want to say I'm really grateful to Shamu and to Dave and to the Minverva Foundation and to Robert and Louisa Fernholz for this great opportunity. So it's and my intention of this lecture, so as already Dave and Shamu explained, it's going to be 10 lectures. And the 10 lectures, for those of you who choose to come, right? So 10 lectures is a lot, and you really get an overdose of the subject unless you sort of, unless for some reason you care about it. And so my intention in these lectures is therefore it's also Friday night, and I felt like we should probably try to go a little bit slow, because if you get lost in the second of 10 lectures, then somehow it's some generosity of Fernholz Foundation to be wasted. And so I felt like I'll explain the gist of the correspondence today, really the simplest possible example, and then maybe I'll just indicate the general feature. And then we'll slowly unravel what the ingredients are. So the correspondence is going to go between quantum groups, but maybe more specifically quantum. I forgot that. Okay. One side, and can you see what I'm writing? Okay, good. Cohomology. Well, we'll take most of the lecture to explain what these things are in the simplest possible instance. And before I start, if you see this starts out like all having the same ingredients, like Google who made this connection, because well, cohomology is associates the topological space a group, and so for the quantum cohomology must be a quantum group, and so here you go, and so but it's not like this, and it's slightly more profound. And so I'll start by explaining what a quantum integrable system is, again by example. So the simplest, if you argue that the simplest possible quantum integral system is, to be precise, the spin on Heisenberg chain. So what spin refers to the highest weight of with respect to the rotation group. And so if I take the defining representation of SU2, which is a double cover S of 3, and from the S of 3 point of view, this is highest weight 1/2. Anyway, so this is a chain of quantum particles, each of which can be two possible states, spin up or spin down. Something like this. And so, so the Hilbert space, if it's length m, then the Hilbert space is just so each of these can be in two states. The one particle say C2, and this is unfold and the product of C2. So now to specify a quantum mechanical system, I have to give you an operator with the energy operator. And the energy operator will be, so the energy will be an operator here. And we'll have the simplest possible form. It will be sum over all neighbors, sum over all I. And there will be some interaction of the ith spin with its neighbor. So some interaction. The ith spin. For this interaction, I'd like to be this interaction. Here. So this interaction is an operator in the tensor product of two C2s. So operator. It's a matrix. And I'd like it so I did with myself enough room to write the most important thing. Like it to be invariant under SU2. It's invariant under SU2, it's also invariant under GL2. So, and there's only, this is the sum of two reducible representations, the symmetric and anti-symmetric. Therefore, the space of invariant operators that invariant there is two-dimensional. And so it's just, so this is, it's therefore some constant, which doesn't matter what it is, times that 1, plus some other constant, like permutation. We could preview the fact that that's invariant, confused with the action of C2, and if we write this with everything. This constant, of course, 1 is in material. If we add 1, it doesn't change anything. And this is it's really just sum of permutation. You might set this constant from 0 to 1, opinion of and so, in what sense this is this system is integrable? Now, again, I'd rather not try to give a definition of what it means to be a quantum integrable system. but instead I'll just say the most important feature of it, and then you'll all agree on this possesses this feature that must be true. So what's the most important feature is that this the most important feature of this is that this space H is a representation of a certain algebra, which I'll denote called gang. What this thing is, we'll discuss the details of what a Yankee is next time. For those of you who choose to come next time. And incidentally, next time is half an hour later.
Half an hour later, yes. Because it shows the lecture in the institute. Then at 4:30, so the lecture here will start at 5 o'clock. No, sorry, 6. Yeah, 5 o'clock.
5 o'clock.
5 to 6.
Oh, this is, so I'll just describe the most important feature of this. This is a Hopf algebra deformation of the universal developing algebra of the Lie algebra, which is polynomials with values of SL2 value polynomials. These are polynomials with values in the algebra. If you take polynomials with values in the algebra, you can just coefficient-wise commute. It makes it a Lie algebra. Now, universal developing of a Lie algebra is a beautiful structure. In particular, the Hopf algebra means it can act. I mean, if you have a we'll get to that. And it turns out that there is, while this object doesn't have, while they have the universal developing, it typically doesn't have so many non-trivial algebra deformation. It does have, Hopf algebra is an extra property, and this Hopf algebra deformation has very non-trivial deformation, and this is, we'll construct this explicitly next time, but this is called the Yankee. And so what's the most important feature about Hopf algebra? That if I have some algebra, then there is no way, if it's just an algebra, there is no way to make a tensor product of two modules a module. Because if you have to make a tensor product of two modules a module of an algebra, you need to have a homomorphism from an algebra to its tensor square. And it's an extra structure that precisely what Hopf algebra precisely means. You have some structure which is co-multiplication. So if you have a group, then there is a map, the diagonal map from the group to the product of the group itself. And therefore, if you differentiate, you have a map, the same map from a Lie algebra, and then this defines a map from universal developing of a Lie algebra. And so this space H is really a product. It's really C2, which really is a tensor product of modules, which is n-fold. Where this is a deformation, this as a module over this algebra is a deformation over the simplest possible module over this algebra, namely there's a homomorphism from polynomials. You can just evaluate set c equal to 0, and then you go to SOP. So if you have a matrix value polynomial, you can evaluate that the matrix and representation of that matrix, you can get the representation of this object. And this thing deforms. This becomes a two-dimensional representation of this algebra. You just tensor multiply, you get a, since it's a Hopf algebra, means you have a homomorphism from the algebra to its tensor square means you can make it direct on tensor products of modules. And so this defines there is an action here. And the point about this action is that there's a big inside so there's not already this algebra contains a very big commuter subalgebra, which then in representation is going to go. This is going to go into a commutative ring. So this image of this D contains my algebra. So it's not just this somehow. It's not just it's not just this operator fits into some big commutative family, but in fact I can get this big commutative family by saying this is a representation of some algebraic structure. In my algebraic structure, I have a big commutative algebra. Already in this abstract structure they commute, and then if I evaluate representation, I get some big commutative ring of operators that contains mine. And it's using so it's make sense so far to what I said? No, just describe it exactly. Yeah.
So image of B and E are in the same place, but
contain.
Yeah, but they're
operator.
oh, it's an element.
It's an element there. Yeah. So you would say these are the quantum integrals of motions, and the point is that it's not just in the when you say quantum integral system, if you say just big commutative family of operators in the space, it's slightly meaningless because a typical operator, you take all of its powers, it's already going to span the maximum commutative subalgebra. So that's not very interesting. But it's interesting when you can. But what's interesting here? First, you can write these integrals in a way which is not involved taking powers of your operator, and also you can write like raising and lower operators using your bigger non-commutative algebra. Not only you can diagonalize your operator, you can work well like that. There's a lot more structure. And so in fact,
so what's image of B a subset of? I can see it.
Well, this is a subset and endomorphism.
Is there a way to generate B from E that's constructive or understandable?
No, not really. This is no. No, like for example, if it's a this is
Casimir's would think about
Wait.
an operator.
well, there is a way, but so there is a systematic way to write this commutative algebra, but it's somehow not in terms of ether.
Not below.
Yeah. Okay. Other questions? All right. In fact, these subalgebras can. So if I have a commutative subalgebra, you can ask, well, you know, like, how many, is there some deformation? Of course, up to conjugation. Conjugation is not interesting deformation. Is there some, do they in fact come in families? Like, for example, if you ask for a Lie algebra, you know, like, ask a Lie algebra itself doesn't have interesting maximal commutative subalgebras. We all learn that up to conjugation, they're all the same. All Cartan subalgebras are conjugate. But in this kind of algebra, there are interesting ones which is different, which is not really conjugate to one another. There is a parameter here which I'll denote Q. This is a parameter. And where it takes values in, well, you can say it takes values in the maximal torus of SL2 itself. Matrix of determinant 1, this will be something like Q1 half minus n. And what this parameter corresponds here. So this, as I said, this guys, the way we'll construct them next time, they naturally come with a parameter. And what this parameter corresponds here? It corresponds here, well, nobody asked me, what's the meaning of those? This summation here goes from 1 to n. And nobody asked me what it means. What is n plus 1? What?
It's cyclic right now.
Right. But, you see, since we assume the interaction is invariant under our group, then instead of having interaction strictly periodic, we can make it quasi-periodic. Means we can make, when we come back, we can, this exact same formula makes sense if I take my n plus first space, be not identical to my original, the first space, but in fact differ by some element in the group. Let's say, I'm going to say, I impose instead of periodic condition, I impose quasi-periodic. Make sense? Again, since this is, and then this element here is this element G. So when I go around, I can act by any element of the group, and that element of the group, of course, it makes sense to choose it out to conjugation, because the conjugation doesn't change anything. I might as well assume it's diagonal of this. And then I'm going to get this. So now the discussion is,
so are you saying that would E commute with its Q version?
yeah, of course. Still somehow, so this commute, so this algebra, so now what I want to say is also, this also presumes if I choose this guy diagonal, right? If I choose this diagonal, it's also in this algebra also have some other operator I want to measure, which is also sometimes called magnetization. And so what's magnetization? Magnetization is when I go over all sides and I just measure whether I have my spin up or my spin down. So let's just say this is summation over I, maybe 1 minus 1, 0, 0, acting at ice. So this state will have magnetization, well, magnetization plus 2. And so this is just an element in the Lie algebra. Inside of this, so the universal of a pelvic inside here, so maybe inside this Yankin, this SL2 itself sits in deformed. When you deform these loops, the SL2 itself that sits here sits on deformed end. And if I take an element in SL2, the way it acts in the tensor product is just acting on every single factor. And so in particular, if I choose one that commutes with my element G, which I chose here, that will still commute with my element, with my entire element. So maybe here for future reference, I always.
So what is notation suggest? Cn plus 1 squared or G times C?
It just means if you take the n plus 1 space, you think you identified n, in this form you identified n plus first side, with the first side by action of the operator G, where G is any inversible matrix. In particular, I can take it to that. It's only after conjugation that somehow. This is what it means to be quasi-periodic. When you go around the circle, you don't come exactly to yourself without the transfer. Other questions? So there's somehow further modification of instead of here where we're evaluating this here the representation was you took a polynomial polynomial balance SS2 and you evaluated 0. You might as well somehow you can denote it by just big C2 of 0. But you might as well replace you can take H to be a product of the C2 value different. Where this AIs could be complex numbers, could be variables. This is called inhomogeneous. You can also, there are further deformation. There's a deformation. There is something called UQ. SO2, called positive deformation. Now, Laurent polynomial. Instead of polynomial, you take Laurent polynomial. More rich to deformation like this. And so, and that has to do. This gives you. So this is in physics lingo. This is called XXX chain, and this is more general XX Z chain. So there's some reason why these things are called this, but it's the reason is kind of ridiculous and then called it. Anyway, that's what it's called. And then for any more generally for any semi-simple group, and then the representation chain. Even less interesting. So what this now has to do with maybe I choose the most important statement written on this pristine board. So now the statement would be that all this quantum integral system and more general ones will have to do something with what's quantum cohomology. Quantum cohomology is the study of enumerative geometry of rational curves in some variety. So, and the variety in question, so this is going to correspond to, so first I'll just say, what's this particular chain, what's it going to correspond to? So this will correspond to here to the side. It corresponds to, and right, I haven't given any reference, of course, I didn't mention names other than Heisenberg. Of course, this is extremely classical chapter in mathematical physics, and in particular, this algebras P are called sometimes beta, sometimes Baxter algebras. A lot of people are now very important work on this. But somehow the fact that this will have to do something with rational curves, well, certainly explicitly in this example, and this is just a generalization. This will certainly, this particular example is just explicitly worked out physics literature sense worked out. So this is the work of Minverva Distinguished. They propose, they also, there are papers, if you can read them, it's clear that they propose a much more general correspondence, and then once these things are, once these things are, once people started, like proving this kind of thing, which I haven't stated yet, it also became clear that other conjectures made in particular by this Okounkov and his collaborators extremely relevant to this, and we'll get this maybe not somehow further down the road. And then the proofs, the existing, a large chunk of these conjectures are now proven, and it's in the work of Danish Molly, who was a great student here with your humble servant. So they'll mention many other names as we go on. But but once we get the contours of the general picture. But right now let's stick to this example. And this, so quantum cohomology is the study of enumerative geometry of rational curves in some variety X. And so what is X? X will be X here. So so I'd like to think, so X will be the following thing. It will be disjoint union. So this takes a lot of custom to this. It's a good thing. So an algebraic right just takes disjoint union. Typically, it's the stupidest thing you can ever take. But then later you'll realize this is kind of a nice feature. This disjoint union are all K of cotangent spaces of the Grassmann variety of k-dimensional subspaces and n-dimensional space.
So fix n.
Oh, n capital. N was the length of my chain. So in my age, in this case, age will be identified, well, not always identified, but will be identified with cohomology of X with complex coefficients. So if I have disjoint union, the cohomology is direct sum. So this means direct sum of the cohomology let's have some abbreviation. Let's have this symbol, denoted whatever. TG. The particular individual name. And so what these pieces have to do here? Well, these are the pieces of my fixed monetization. So if I decompose, if I look at these, so these are eigenvalues. These are eigenspaces. So if I look at if I have n spin, then I have k of them pointing up, then the dimension of that space is n choose k, which is also the dimension of the cohomology of the class many. And this is do you see something more on how? And of course, as long as if we talk about ordinary cohomology, there's no difference between the space and the total space of a bundle over it. So you might be wondering, why did I put the cotangent bundle and not the point that quantum cohomology is a new structure which is not homotopy invariant. And so the space and the total space of a bundle over it is a very different thing. So with quantum cohomology is a new product. The new associative algebra structure. On right, so before we go there, before we go define it, a word about what sort of cohomology theory I'm going to take here. And so now I don't want to pedal on this right now, but it will be extremely important what follows that we work everywhere we work in equivalent with respect to all automorphisms of X. And there's a cohomology theory called equivalent cohomology that is particularly well adapted to this. And we'll review this, whatever element of this theory later in the lecture. So you have to take if you're not familiar with it, you have to take my word for it now, that this is a theory which is easier than ordinary cohomology. It's much easier to do equivalent computation than to do ordinary computation. So, this is really, if you have a group action and you keep check on that, that always works in your favor, never works against you. Group is always your friend. So this would be, in many ways, this would be with respect to some group of automorphism, to some group, which we denote, I haven't used G yet, so we can use it now, G. G of X is equivalent group. Cohomology. And it's always, this thing is always a ring, so it's always an algebra over the creative cohomology of point, which is the same as the invariance. We take the polynomials of the Lie algebra, we take the invariance. So the eventual tree, which is somehow, you'll see there are some technical details which don't quite work out yet in K-theory. A dream would be to in fact work in a current K-theory. In a current K-theory would be just computing indices of some push and somehow let's say all the characteristics of the bundles. We had a group action on a bundle, then the resulting Euler characteristic is the representation of the group. So it's naturally a function on the group itself. There's an approximation to this, which is according to cohomology, where instead of getting a function on the group, we get a function on the Lie algebra. And we will review this. It's not hard. It's always easy. So point of that is that this you can get there. And right. So point is that if you extend, if you enlarge your, if instead of working with this ring, you enlarge your ring a little bit, then you have like Poincare reality given for non-compact spaces. So you go this is. I mean, they are pairing for non-compact spaces. So now, so I get so defining a new algebra structure. So this is a new product. So what is a new product? Which I'll have a structure which is star with notation for the product. So the definition of this is like this. It's not going to be definition. It will be definition in the same sense as this is the definition of the Yang, and this will be the definition of the product. So if I take one class alpha, and I want to multiply some other class beta, and then to find out what this is, I'd like to pair it with some other form gamma. So this is the old, where the pairing, the usual pairing. This is a new product, but this is the old pairing. This entire discussion with cohomology was because for non-compact spaces, for some non-compact spaces, I still have a well-defined pairing in a creative cohomology as long as I have so you see like a non-compactness here comes from of course the fibers of this cotangent bundle, but there is an automorphism which just scales the fibers, and that makes this well-defined. And so this is defined like this. This is the sum over all classes in H of X, H over 2 Z. Now here you can put just a formal symbol if you like. Q to the T. We'll discuss the meaning of this symbol in a second. You can think of it as a function, so let's put it like that. Right now, let's do a formal symbol. And then the number of parameters cycle Poincare dual alpha. And so assuming the dimension work out, so that this expected number is 0. I mean, define it. It's the so alpha check is the cycle Poincare dual to alpha. Alpha is cohomology class, the cycle Poincare. We'll give a better definition in a second. Somehow, the way you're thinking about this is the best. So take.
You mean the do integration of alpha?
Right. Well, somehow. Okay. So if you're worried, I'll just simply write another definition. So, we'd like to say, we can write the sum over T. Consider moduli space and bar. We discussed what bar is, and bar is 0 is 3x. T is demodulated somehow. LD here are maps of a 3-point sphere, a 3-point rational curve. I call it a map F to x and degree T. A 3-point rational curve, mapping to degree T, and so what you'd like to say that this product is continuous right here, sum over T, and we take the integral in some sense over this some kind of fundamental class of this. Again, we discuss what this means. And so whatever this guy comes with evaluation at the marked point. There are 3 points here, T1, T2, T3. This moduli space comes with 3 maps to X, which by evaluating F at this marked point. And what you do is you pull back from the first evaluation map, you pull back class alpha, and you pull back. Double definition, except we need to discuss what this is for. And this is a cycle of a certain the cycle of some degree, some dimension, and the dimension of this cohomology class has to measure the dimension of the cycle, so otherwise it's going to be 0. Yes, Q to the D. Let's start with Q to the D. What's Q to the D? Q to the D, first, there are no rational curves in some homology class unless that class is effective. Inside of all homology classes, there are the ones which are actually represented by rational curves form a cone. It's a non-degenerate cone inside. There's no, let's say, x-axis is quantum projected, for example, then it's impossible to have a curve in the opposite direction to be both effective. So this really is inside some effective cone. And the easiest thing to think about is Q. Q to the D is just an element of the semigroup algebra of this effective cone. I mean, it's just some symbols that if I multiply the symbols, the class is F. But of course, if you're somehow, all of these considerations came from considerations in like an actual physical problems, and then there, of course, these people view this not as a symbol, but rather as a function on the operative of X. You say this symbol, T, it's really X, but you weight a curve by minus its area. So you integrate over by class D, you integrate some form, some area form. This then becomes a function. This is an element. Again, this is an element in chapter 2. Becomes a function on some subset in upper chapter 2 when this series conversion. But like I said, for us, it's best to think of this as a variable. So Right. So again, there's something I'd rather not explain today, and in fact maybe I'd rather not explain these lectures at all, is how you actually construct a suitable cycle. There's something called, this space can be, I should be like the last person in this department telling you that this space can be pretty complicated, and but one has one redeeming feature. So you can construct something called virtual fundamental cycle. This is a cycle. We'll discuss what expected dimension is. Expected dimension is some number you get from Riemann-Roch computation, and then it's proven in Janus's book that every component is at least this dimension, and you can construct it in homology of that component. You can construct in homology of the space. You can construct a canonical cycle. There's also in fact a covariance cycle, and then against which you can integrate. So that's and right. And so what's the miracle about this definition? The miracle is that this is associative. It's obviously commutative because alpha and beta plays exact same role here, just renaming the point. But the fact that it's associative, it's not hard to prove. It's a wine-line argument, but it is a miracle. It's an associative problem. This makes this associative. I mean, this is one of the many nice features of so example. Exercise and spell this word is too complicated. So exercise. So compute this for projective space. And what is this product for projective space? So let X be projective space of X, and then let H class. And then if I look at the operator of quantum product by H, that in the basis I choose in the basis 1 H squared up to H to the n. Point. So in this basis, this quantum product has the following form. So it's obviously zeros on the diagram. And then one just below that, as it is in classical product. And then the only new quantum term you get is this one here. It's the only term you get. So what this Q signifies here, but if I have, what would I have to do here? I have to take one point, so which is the last basis element was a point. So this is my alpha, which is the point. Then I have to take get the first one, which is 1. That is the dual of gamma. So another point is the dual of gamma, where gamma was the identity. And so then I have to look for a rational curve, and then I have a hyperplane, so that says there is a unique line that meets meets 2 points, and the hyperplane is given point. The hyperplane. So in this computation, 2 of my guys are points and 1 is a hyperplane. And I am asking for rational curves that with 3 points that meet point, and a hyperplane that is unique. And all others are 0 for dimension reason. So this expectancy, so this is how I'll give you a formula for this expected dimension.
Before you erase,
What?
is there a relation between that Q and the Q that you just erased?
Say again?
Is there a relation between the Q on that board and the one that you just erased?
Yes, that will be the whole point of the discussion. Yeah, yeah, we're getting there. Yeah. This expected dimension, which you get from Riemann row, will tell you that this is the dimension of this space, expected dimension of M0 3 bar T is dimension x plus C1 of x to T. And so this is from this formula here you can work out that there's all other ones which is 0 for dimension. And somehow what will be important for us is that if you have a variety which either or this cloud is either positive or negative, then this series will not terminate for dimension reason. So there is this here, the only thing that varies is t. And so the dimensions of this alpha, beta, and gamma are all the same. So if this thing either the gross or t case with t, then eventually we only find right. So if this number is non-zero, if this pairing is non-zero, this one, then the series will be finite for dimension. However, the varieties we will ever encounter, for all of them C1 will be 0. So for us, the series, so for us, this will be always 0. And in fact, as it is for the potential progress making. In fact, all about varieties will in fact be symplectic, not just with trivial canonical. And so then something nice happens that the degree computation, dimension computation, it's quasi-projective. I mean, I never said it's projective. You can be, in fact, it can be defined quite generally, but I say let's assume X is quasi-projective.
How do you define it?
I mean, this is as long as you can integrate. Yeah, that's fine. I mean, any theory in which this integration is defined is fine. Like for example, it could be that variety is non-compact, the space of curve is compact. That's it.
So how do you? So when you would say one of x, you mean for quasi-projective variety?
Say again?
I'm worried about this
Well, I
one.
don't know. C1 of x is a well-defined thing. So for us, the dimension calculus works just out. For comfort. And what's the cup product? The cup product is the same thing, right? I didn't say. When you look at the degree equals 0 part, the corresponding moduli space is canonical X itself. Because the map of degree 0 is just a 3-pointed sphere mapping to a point in X. And there's unique size for every point in X. And so in particular, the zeroth term in this series is the cup product. And the cup product is defined as the cup product. This is the cup product, and this is this integrated against X. This is extremely important. This is why I said it's deformation of the cup product, and the reason it is deformation is the zeroth term of the series is the cup product. Is that clear, everybody? The zeroth term of this space is X. These evaluations are just nothing's going on. It's just, the one-shot space is just 3-pointed sphere collapsed to a point in X. This pullback of evaluation is just nothing's going on. It's just a product. You multiply 3 cohomology plus integration against X. So dimension counts work just exactly as this. The gradient in cohomology is just what it is. And in particular, for us, the series, once it starts being non-zero, it's typically non-zero always. It's going to be an infinite series. Now we spoke for about an hour already, so we come to some kind of final have to be defined enough in greeting to say what's going to happen. So I have the board here. So what would be the statement? So the easiest statement to make is the following. Here I have the space H, and inside of endomorphisms of H, inside of endomorphisms I have this quantum fields of motion. The operators act on H, motion, but it's the same as the image of this subalgebra Q. Now the statement that this thing is equal I haven't told you how this identification is going to go. I mean, there's a lot of part I haven't told you. I'm saying there is a natural identification which we'll construct in due course. Such that if I take the quantum integrals of motion here, then this subalgebra will be equal to the algebra of operators of this product. So each of these spaces is now a commutative ring with a new commutative associative structure. So if I have a commutative ring, then I can have operator just multiplication by elements of the ring. And this, for trivial reason, forms like a maximum. If I have break rings with identity, this is a maximum commutative subalgebra of a ring. And then I say these things are equal. There's more. There says, which if I take natural geometric operators multiplication by some natural geometric classes here, they will go to some special operator instead. But this is somehow this is like the first step. And with the identification of parameters, that this Q here. Here Q was this has to be this quasi-periodic boundary condition. And here Q For Grassmannian, so for Grassmannian, this h over 2 is one-dimensional. So so it's just really one parameter, and q to the d is just really the group. So the semi-group algebra of the effective cone just represents one variable. That's q. And now you see that this is why this correspondence has somehow so slow in being discovered, and why it's not a deformation of something already known, why it's not just a purely quantum effect and not a deformation of something previously existed. Because here, of course, when people think about quantum cohomology, they naturally think of this being a deformation of the situation. Somehow the classical limit as q goes to 0, classical limit here. And somehow to recover classical cohomology, you'll set let q go to 0. But this is just completely absurd here, because here you took a quasi-periodic boundary conditions where q was twisting, and you make a limit. In other words, here you take a limit of the periodic boundary condition where they over-twist to. You see what I'm saying? You consider, as you go around the loop, you multiply by 5 billion. And those people typically don't do that. And usually you pick a phase, but not at all. And conversely, here somehow the natural the natural parameter people were certainly aware of the quasi-periodic boundary conditions, but what people normally study, people somehow typically interested in, is ordinary boundary conditions. Typically we think, well, q maybe go to 1. It's like the natural limit to study. You naturally view this as a perturbation of q equals 1. Whereas q equals 1 means this infinite series will be like the most possible divergence. So this is an infinite series, which in fact, so for a general variety x, there's nothing known about the convergence of, suppose I have a general variety and some class that pairs 0 with C1. As far as I can tell, there's nothing known about convergence of this series. Here we will prove that this is a rational factor rational function, but q equals 1 is a total that rational function. And so this is certainly not a, here q goes to 1 is certainly not a very natural point to look at. And certainly q being on the unit circle, which is another, so typical from people in this branch of mathematical physics, for them if q is not 1, then it means of the absolute value 1. This is certainly not a very good point to study here. Because all of this is really not general. And so why is this maybe I'm a little bit out of gas to explain why this is great. After all, this is not maybe a little bit of more work. Why don't we take a 1 minute break?
integrability of the model is somewhat unusual, exceptional, and there are some very handy consequences.
Right.
Could you point out to specific implications of integrability of this version of quantum integrability for, say, the Heisenberg model? Anything? What does it facilitate in some sense analysis of the spectrum, time evolution generates? Whatever.
So, sorry, what's the question again? So certainly,
what do we gain in understanding of the quantum Heisenberg model?
From this perspective?
Yeah, from the quantum integrability.
So okay, so this is going to be like a very specific, extremely specific answer. So I mean, as Michael correctly pointed out, integrability is a really kind of miraculous feature. I mean, it has, forgive me for saying it, but I think it has nothing to do with. It's more like the physics of, the large-scale physics of an integrable model and nearby non-integrable is the same one.
Well, quantum chaos theory.
Yeah, right. So right, the quantum chaos, yeah. So, but anyway, it's just some kind of extremely special feature. And of course, this been studied forwards and backwards for many aspects, and of course, the big machinery of this quantum cohomology is not going to shed a whole lot of light on finite dimensional spin chains. It will help in two aspects. It will point towards the right generalization for, like I said, this you can define the spin chain for any Lie group and any representation. But then you can ask, why do we have to be content with finite dimensional Lie groups? So, and in fact, so if you pursue this analogy, you'll be naturally led to infinite dimensional Lie groups, which are not custom Lie, something more interesting. And the corresponding systems you'll discover there will be like, the simplest one beyond finite dimensional will be certainly integrable quantum hydrogen. Like for example, you'll be able to integrate the quantum intermediate long wave. So intermediate long wave equation, you'll be able to integrate that. So like as far as I can tell, the spectrum of that was unknown. Was not. So and many more general things, which not systems of finite dimensional version. In the statement in the theory things with fine dimensional things. That one thing that helps, it clarifies the theory of Baxter Q operators. And the theory of Q operators is something. I certainly find this kind of geometric perspective a little more illuminating than pure algebra. But it's of course in all honesty, this whole story of quantum cohomology is not going to add much to our existing knowledge of like speech. It's the whole information the other way around. In this case, of course, like one side, the Heisenberg magnet, that of course, that's studied in such great detail. There's so much known about it, and quantum cohomology of Grassmannian, it's not like the hardest object in math. Well, of course, a respectable mathematician wrote complicated papers about the quantum cohomology of Grassmannian. That's a subject that, if you think about it correctly, it's kind of easy. Yeah. So in this particular example, the correspondence is easy, and it's not relatively easy, and it's not either way. It doesn't say. It's not like you have two relatively well understood, relatively simple things. There is a certain amount of flow of information, but it's limited in this example. But it does illustrate the general features to which I'm going to turn now. So, what are the general features? So when do we expect some kind of integrable structure in the quantum cohomology? So expectations. close to 6 o'clock on Friday night, this would be slightly important. And so approximation. Right, sorry, I apologize. I didn't say the most important thing. Then the whole other parameters, and here's, sorry, I apologize, let's go back here. Then the inhomogeneities of this, so here there were inhomogeneities. Here they, so this is everything. Here they group the what acts of the Grassmannian. Well, the Grassmannian acts GLN acts on X, and this has, so in a covariant cohomology we have functions of n parameters which are n eigenvalues, and this of course would be this inhomogeneities of the Heisenberg chain, and so on and so forth. So there's complete match of parameters on all sides, and the covariant variable that scales the fibers, this is going to be the deformation variable of the Yang. Yang has this deformation variable, which I set to 1.
Did you define
what?
I missed it. Did you define it before?
No, I specifically said that. So this is going to be, this will be in the remaining 10 minutes. I have to give some sort of idea what the general picture is going to be. And so, in other words, in which, well, maybe I say, so in which, we have X, we look at these operators, and is like, when can we find representation of some algebra with, when can we find the structure of Plankton's cohomology? And so approximation is that X has to be, it's not, I don't think it's the final answer, but the approximation X should be what's called equivariant. Well, it means the first thing it wants has to be algebraic fraction. e.g., contended model to something else. Second, it has to be a resolution of singularities, meaning that if I take the maps from X to the stack global functions, so this is say like all global homomorphic functions, all global functions of X that defined with some map, and I'll take this map, so take the global functions. This is projection in Parashi. Incidentally, there's a long-standing conjecture, I think it's still a conjecture, that if I have cotangent model for something such as this is projected by rational, or this is a homogeneous array. I think it's still a conjecture. And then third, so here it's easier to say what the resolution is, not what the singularity is. Some variety. And so incidentally, what is important for Tsar-Grassmannian? Tsar-Grassmannian, if you think about what's the global functions of it. The global functions in it are in fact generated by the moment map from the action of this X infinity way. You look, the corresponding moment map is going to go to Lie algebra. And then the image of this will be matrices with square 0. And the rank of this matrix is so this is for Grassmannian, this thing are matrices of squares, so this is matrices of size n squared 0, rank m is the minimum of k and n minus n. In particular, the Grassmannian and the dual Grassmannian do different resolutions of the same. Third, more important thing. scaling omega by unknown triple. So here, in this example, so there's the Gillian part preserves, Gillian actual debates and preserves these subtractive parts. But the part that scales the cotangent fibers also scales the form. Alright, so these are the conditions. And I'm sometimes quoted as saying that these are the Lie algebras for the 21st century. And I'd like to at this point say that the century still awaits its Cartesian killing to classify these guys. And but there are many examples. So examples, there's examples. Most interesting examples in two flavors. One is in fact cotangent bundle of continuity. This is an example. Because cotangent bundle. And this is always a resolution of some important orbit. And the second example, the intersect. So, second example, the whole this is associated to an arbitrary, what's called quiver, or some generalization of the diagram, drawing in a graph like this, and associated some variety with it. So that would be sort of your Dinkin diagram. And if you start with the Dinkin diagram of SL2, which is 1 point and one dot and no edges, then you also get this diagram. And so, it is about how the lecture will focus on this. Well, at some point in one of the 10 lectures will review what an academic currency is. It's a useful thing to know. It's really beautiful currency. So then of course with Nakajima varieties, the statement is exact same, where instead of SL2, you replace SL2 by whatever you fancy associating. There's some Lie algebra you associate to this thing. If this thing was an ordinary Dinkin diagram, you'll learn the Lie theory class. That will be the corresponding simple Lie algebra. But in general, it's something. And in particular, among like if my graph, so this is my if then Q is 1 dot, then among Nakajima varieties one finds, sorry, Nakajima corresponding Nakajima varieties. They include, so these are modular. In particular, the Hilbert scheme. And this is why it's so interesting from the point of view of people interested in threefold. Because if you study rational curves in sheaves on the surface, you're really studying sheaves on threefolds. The threefolds that fiber in that surface over a curve. And so this lets you access the information. But I mean, this is a lot of people care about numerative theories of sheaves and threefolds, and this is at the moment the best way to. In fact, the best way to access it through this to explain. And purely from the point of view of purely like representation theoretic viewpoint, this is also the case where the corresponding Yang, and so this dissociated the corresponding Lie algebra associated to this quiver is in fact, so to speak, loops into loops. Sorry, this is, I apologize. The corresponding Lie algebra is this, and then you when the Yangian would be loops into loops. This is like a loop, and Yangian is one loop. And this is where instead of finite dimensional representation, you start getting representations look like function spaces. And this is instead of spin chains, you find equations which are highly dynamic. All right, so that's an hour and a half. Yes, exactly.
There will be no introduction next time.
What?
There will be no introduction next time.
No, but I mean, the idea is that somehow we're going to start slowly. So next time, my plan was to just explain what like the Yang is.
Okay.
And first I'll do, and then, take it slowly. It'll be a while before we can.
Lecture is a video tape. I don't know if it's make available soon.
Soonish. Yeah, we'll see.
Yeah. Next week is 5.
Was I the video?